Hey guys, welcome to the final stage of the class project, which is our final report. We had an amazing semester, learning a lot down the road. As we see, our project studies on cardiac disease prediction based on one symptoms. I would first like to introduce our group, Team 76. Praharsh Patel, Rishi Chilara, Hargopal Chaudhary, Andrew Zhang, and Kewal Khalsi. Our team has been great and supportive of each other throughout the semester, making this possible and our project successful. I would first like to start with an introduction of our project. As we know, the leading cause of death globally is caused by cardiovascular disease, which makes up for up to 33% of all deaths worldwide. One person dies every 34 seconds in the United States from cardiovascular disease, and it costs the US almost $229 billion every year, which is a great amount. It would be viable to detect cardiovascular disease as early as possible so that management with counseling and medicines can begin. We can help prevent individuals prone to having cardiovascular disease through initial alerts and support by their symptoms. Our team wants to focus on tackling this problem by identifying the presence of cardiovascular diseases based on patients' personal health data. To tackle this problem, we use dataset heart failure prediction dataset from Kaggle, which has 11 attributes and outputs if the person has heart disease or not. Our data collection comes from Kaggle. We have combined 5 independent heart disease datasets to support our case. Through almost 918 observations, we have an affirmative research that shows the reasoning behind knowing symptoms and how it helps to aid others facing cardiovascular disease. There are some problems within our data that arose while doing our research. We then reduced PCA from 12 to 8 features. We implemented backward feature selection, one hot encoding, and normalized data. For our project, the methods we will be using are the following: simple feed-forward neural network, logistic regression, and naive Bayes model. The dataset is already labeled, therefore this method would be perfect for supervised learning. Now I'll pass it on to my teammate Praharsh, who will explain the models and give some analysis to each.
Thank you, Hargopal. And now I will be going over the methods we used. The first method we used is logistic regression. Logistic regression is a very basic model which can be helpful in analyzing and completing binary classification algorithms. A Bayes logistic regression model led to a ROC curve and confusion matrix heat map as seen below. The ROC curve shows the true positive rate versus the false positive rate, and a closer accuracy value to 1 indicates a better fitting model. With logistic regression, we achieved the accuracy of 0.85. The next method we use is the naive Bayes. We used a Gaussian naive Bayes model to fit the continuous features of the dataset, and a categorical naive Bayes model was fitted to the discrete features. We combined them, and this resulted in MSE of 0.1847 and an AUC of 0.87. The last method we used was a feed-forward network with a k-fold hyperparameter tuning. We made a 5-layer fully connected neural net and trained using stochastic gradient descent. We used the grid search CV to help tune the hyperparameters of a fully connected network and found our optimal parameters to be batch size of 32, epoch of 200, momentum of 0.2, and learning rate of 0.001. We achieved 93% accuracy with this test set. Now we'll move on to comparing our models. Across all models we've seen, our main metric of accuracy, the tune feed-forward neural network performed the best. This comes at a cost of lower recall for the no heart attack class. Recall is an important metric considering what our model will be used for. In medicine, a false negative could be life-threatening. This also came at the cost of large computational cost of training the network. Naive Bayes was the simplest to implement and cheapest to train. But as our feature space was relatively large and our data was more correlated than desired, it struggled. This was partly due to the underlying assumption that all features are independent. Logistic regression was the great tool for our task of binary classification. While it still did a fine job of 85% accuracy, it fell short of the tune feed forward network at 93% accuracy. It increased performance over naive Bayes, which can be explained as logistic regression performs relatively better if the dataset is more correlated. Since logistic regression does not have as many hyperparameters to tune, the current performance could only be improved through better data preprocessing. All in all, working with these models gave us a fantastic insight into the world of classifications. Working with the simpler task of binary classifications gave us an opportunity to create a high accuracy model by allowing us to focus on improving the network. There are several more models that we might try to implement if we decide to continue researching this topic. Models such as SVM or maybe even some unsupervised tasks. And that would be it by Team 76. Thank you.